So in this video, I want to talk about boiling points and melting points. So first, what's going on with melting points and boiling points? Well, we know if we have this solid, we know we can add heat. We know we can add heat to the solid to melt it. And then the solid melts into a liquid. And then we know once we have a liquid, we can add more heat. And if we add heat to this liquid, then we know the liquid evaporates. So this is something we're probably pretty familiar with, but what's going on here? Well, why we add heat and then this melts and then we add heat and this evaporates? What's going on? But really what's important to note is when we have two compounds, we know they can form bonds. And when they form bonds, even if it's an intermolecular bond, we know that's favorable. So therefore, that's energetically favorable, forming those bonds. So therefore, to break those bonds, to go in this reverse direction, that's unfavorable. So therefore, to break these bonds and to go in this opposite direction, we need to add energy. We need to add heat so we can overcome these bonds and break these bonds. So that's what's going on. Whether we're melting or we're evaporating, we're adding heat to break these kinds of bonds. However, what determines if this compound has a high melting point? Or what determines if maybe it has a low melting point? What are the kind of properties, these physical properties that determine if it has a high or low melting point? And something important to note, if this compound has a high melting point, it probably has a high evaporation point. Usually those things correlate. It can get a little more complicated because when we evaporate something, the molecular weight of these guys have an impact. Because again, if this has a high molecular weight, it won't evaporate very readily. So maybe it'll have a higher evaporation point, boiling point. But again, so what determines if this has a high melting point or a low melting point? Well, let's look at some key examples you'll see in an organic chemistry class. Here are these positively charged or ionic compounds. So these ionic compounds would have a high melting point and therefore a high boiling point. We would have to add a lot of heat. We would have a very high melting and boiling point, so therefore we would have to add a lot of heat to break these bonds. However, this would have a lower melting point and boiling point to break these bonds. This would have a lower, and then this would have a lower, and etc. And this would have the lowest. This would require very little heat to break these bonds and for this kind of thing to melt or break. And again, remember, I'm just showing two of the compounds, but again, we would have millions of these compounds forming these intermolecular bonds, which would again create. So these are physical properties. These are between two kind of compounds. These intermolecular bonds. So if we add heat with this kind of mixture, we would have to add very little heat to melt and to melt this guy. However, maybe this guy would require a little more heat to break these intermolecular bonds. This would require more heat to break these intermolecular bonds, and this one would require a high amount of heat. So what's going on? What's the pattern? Well, really all that's going on is the polarity. We see these are two very polar. This is very positive. This is a full positive charge and a full negative charge. So this is very polar, forming those favorable ionic coulombic interactions. So therefore, in order to break this bond, you need to add a ton of heat. That's why it has such a high melting and boiling point, or this is the melting point, so that's why it has such a high melting point. You need to add a lot of heat to break these bonds. And again, these are all theoretical melting points, but again, the point is just to show you these trends. So again, this is very polar, so it requires a lot of heat to break those, because again, these are very energetically favorable bonds because they're so polar, these favorable ionic interactions. So therefore, to break it, you need to add a ton of heat. So that's why it has a high melting point. However, these guys are also pretty polar. They don't have full formal charges, but they have partial charges. For example, this oxygen is partially negative, and this hydrogen partially positive, and this oxygen is partially negative, and this is partially positive, and then these carbons are partially positive. But again, so we do have some partial positive and partial negative charges. So we have some of those coulombic interactions. So therefore, that's why it has a fairly high melting point. We do have to add a certain amount of heat. They don't have as favorable interactions as these full formal charges. This one requires a ton of heat to break, but these are pretty polar, so it requires a decent amount of heat to break. So again, however, these have a lower boiling point and melting point. So why is this melting point lower? Because it's less polar. This one is very polar, and this one's a little less polar. But really what's going on is because really these are pretty similar. So why is there such a drastic change? Because we have hydrogen bonding. And we know, we've talked in previous videos about hydrogen bonding and when you can catch if there's hydrogen bonding. But this does have hydrogen bonding, and hydrogen bonding is very favorable. It forms very strong intermolecular bonds with this hydrogen bonding. So therefore, these hydrogen bonds are very favorable, so therefore this requires a lot of heat to break these bonds. However, this doesn't have hydrogen bonding, so therefore requires less heat to break these bonds. This hydrogen bonding is very favorable, so it's very hard to break, so you have to add a lot of heat. So again, that's why we see such a drastic difference. They're pretty similar, but the only difference is this has hydrogen bonding. So now comparing this one to this one, why does this one have a higher melting point than this one? Because again, this is polar. These are polar, so therefore they're polar, so therefore it takes a decent amount of heat. So hopefully you see that trend. This is super polar. This is still polar, but a little less than this. And this is less polar. Now this is not polar at all. So that's why this has a very low melting point. Because again, you have to add heat to break these kind of polar interactions, but this has very weak interactions. This only has weak van der Waals, London dispersion forces, so therefore this requires very little heat to melt this. So that's why there's such a low melting point. And this is even weaker. This has an even lower melting point. Why? Because there's less van der Waals interactions. This has this much van der Waals interactions between two compounds. And again, remember, there'd be thousands of these compounds. But again, this has this many interactions, while this one only has this. This has less of those favorable van der Waals interactions, so it requires less heat to melt this, so that's why it's a lower melting point. And then these don't fit snug at all. At least these fit snugly to create these kind of interactions, these van der Waals interactions, but these don't really fit at all. So this can't really create any kind of favorable interaction. So that's why this has such a low melting point. You had to add barely any heat to melt these guys. So again, just the point is, it's the polarity. The more polar, the more favorable bonds that are made, so therefore a lot of energy in the form of heat is required to break those, so that's why there's a high melting point. So a couple last quick things I want to go over is something else that affects melting point or boiling point. So let's say we have this container. Let's say we have these two containers. And let's say this one has a liquid, and let's say this one has that same liquid. But let's say this one has a low pressure. This is a pressure of 0 atmospheres. And again, let's say they're in different rooms or whatever. So this has 0 atmospheres pressure. Let's say this is 10 atmospheres pressure. Which of these liquids, even though, let's say they're the same liquid, let's say they're both water in both cases, which one would have a higher boiling point though? So yeah, even though they're both water, so you would think they would have the same boiling point. However, this pressure has an impact. This one would have a higher boiling point. Maybe this one would have a boiling point of 100 degrees Celsius, when this one would have a boiling point of maybe 200 degrees Celsius. So why does this have a higher melting point? Well, again, boiling point. Well, again, we have such a high pressure. We have this high pressure. So therefore, remember what happens when we evaporate. We add heat, and then these water molecules will evaporate. They'll evaporate in this region. However, if we have high pressure, it's harder for them to evaporate. We have this pressure pushing down on these water molecules. So therefore, for them to evaporate, we would have to add more heat. Here, if we add a certain amount of heat, then they can evaporate fairly easily. However, here, it would require more heat because we have this pressure affecting them from wanting to evaporate. So that's just, the point is that pressure affects the boiling point. If we have high pressure, therefore it's harder to boil. But on the controversy, on the flip side, if you lower the pressure, then the boiling point decreases, and then it's more easily boiled. So again, so that's just something to remember, how pressure can affect the boiling point. And something else I want to mention is now, instead of focusing on boiling points, let's now focus on impurities. So let's say this one has an impurity. Let's say this is pure water and this has an impurity, so some kind of impurity. Something important to note is, let's say this water again has a boiling point of 100, but this water with this impurity has a boiling point of 200. So impurities increase the boiling point. So why is this boiling point increased? Well, again, the way I like to think about it is we have all these kind of impurities kind of forming this blockage. We have this blockage of all these impurities kind of blocking the surface of the water. So therefore here, if you add heat, then the water evaporates. Then the water evaporates. However, here, if you add that heat, we have this kind of obstacle, these impurities. So therefore, to have this water to evaporate, you have to add in more heat. That's why it has a higher boiling point. You have to add in more heat because we have this obstacle of these impurities. These impurities are kind of blocking this kind of this interface between the solid and this air. So therefore, you have to add in more heat because to overcome this blockage. So that's why you have to add in more heat. So that's why it has a higher boiling point. So again, impurities increase the boiling point. One last thing is, again, so let's say we have this solid with its very strict, very specific kind of organized crystal structure. Now let's say we have this kind of situation, where again, let's say we have the same solid, but now we have this impurity. We have this impurity. And let's say these are liquids. But again, the point is that, so what's essentially my point is that this pure liquid would have a certain freezing point. Maybe this has a freezing point of maybe negative 100 degrees Celsius. However, this with the impurities would have a lower freezing point. This would have a freezing point of maybe negative 300 degrees Celsius. So the point is that impurities decrease the freezing point. So this impure liquid has a lower freezing point than this pure liquid. This pure liquid has a freezing point of 100 degrees, negative 100. So why does this have a lower freezing point? Because again, when something freezes, it forms these organized crystal structures. When something freezes, forming this solid, it forms these organized crystal structures. However, this is going to have a hard time forming those crystal structures because we have all these impurities kind of getting in the way of these crystal structures being formed. So therefore, it's harder to form these crystal structures. It's harder to form the solid, organized crystal structure because we have this obstacle of these impurities. So therefore, if we want this to freeze, it's harder. We have to make it even more cold. We would have to, so therefore, it has an even lower freezing point. It's even harder to freeze because it has these impurities kind of as an obstacle, so it's harder for it to form these organized kind of structures. So therefore, we have that obstacle, so it's harder for this to freeze. So in order for this to freeze, we have a lower freezing point. It really has to be cold for this to freeze. But again, the key point is that these melting point and boiling points, it's usually related to polarities. The more polar, the higher the melting and freezing point, and etc.